Stand in an empty field at midnight, and the world feels solid, serene, predictable. The grass rests where it must, the moon keeps its steady arc, and each breath seems as ordinary as the one before. Yet beneath that hush, reality hums with a very different cadence, one stitched from probabilities rather than certainties, from shimmering possibilities rather than fixed facts. A century ago, physicists fired a thin beam of electrons, particles of matter as familiar as the atoms in your hand, through two narrow slits cut into a metal plate. They expected each electron to choose a single path to land on the screen behind in neat, particle-like clusters. Instead, the screen lit up with a rippling interference pattern, as if every electron had taken both paths at once, then interfered with itself along the way. When the scientists tried to spy on the electron's mid-journey, the pattern collapsed into dull, particle-like dots. As though the act of watching forced each electron to make an irreversible decision, that simple experiment blew a hole clean through classical certainty. It whispered that the universe does not commit to one story until compelled. It hinted at a realm where objects explore countless possibilities in parallel, where measurement is less about reading a pre-written page and more like choosing a single line from a draft filled with alternative endings. Some shrug and call this realm weird, as if the quantum were an optional oddity reserved for particle accelerators and sci-fi plots. But remove quantum rules, and nothing familiar remains. Atoms fall apart. Chemistry loses its periodic rhythm. Stars fail to shine. DNA can't replicate. Every sunrise, every memory, every living cell relies on laws that are, at their root, indeterminate. Consider the emptiest vacuum we can imagine. Even there, fields quiver with zero-point energy, spawning pairs of particles that flash into existence, borrow a moment of reality, then fade. These restless jitters seed the large-scale structure of galaxies and breathe life into every laser pointer, MRI scanner, and smartphone chip. The quantum, in other words, is the operating system. Classical physics is merely the desktop wallpaper, user-friendly, but never the whole machine. Tonight, we begin a journey into that operating system. We'll trace uncertainty not as a flaw in our instruments, but as a principle etched into existence. We'll watch electrons hold two destinies at once, see particles half a universe apart share a single handshake, and learn how the very randomness that unsettled early physicists now powers the encryption that guards your digital life. By the end, you may find comfort or wonder in knowing that every sunrise is the outcome of quantum dice quietly rolling in the dark. The cosmos does not whisper in absolutes. It speaks in chances. And it is precisely those chances that let stars burn, planets form. And as creatures of dust and thought, look back in astonishment at the invisible dice forever tumbling beneath our feet. Picture a dim laboratory in 1909. On one side, an electron gun whispers, releasing charged bullets one at a time. Ahead, two razor-thin slits have been etched into a sheet of metal. Behind them waits a phosphor screen, eager to record each impact. To every classically trained physicist in the room, the prediction is obvious. Each electron must choose left or right, tracing two neat columns of dots, no different from pellets through twin windows in a barn. Their confidence rests on centuries of common sense. Apples fall, planets orbit, bullets fly in single, well-defined paths. Even light tamed by Newton's prisms seemed at worst a curious wave, never both wave and bullet at once. So the double slit is posed as a simple sanity check. Confirm that matter, like marbles, obeys one lane at a time. The first few shots land exactly where expected, bright pinpricks behind each slit. Boredom settles, pipes glow, then hundreds become thousands. Patterns emerge. Faint bands, bright, dark, bright stretch across the screen like ripples on a pond. The electrons are not piling up behind their chosen doors. They're interfering, canceling, reinforcing, as if each one were a spread-out wave exploring two routes simultaneously. Common sense does not crack, it shatters. The experiment whispers a dangerous possibility. Nature does not commit to a single story until forced. Questions sculpt the answers we later record. To test the mystery, the researchers slow the gun. One electron every few seconds, then one per minute. Tiny, indivisible packets hurled through space utterly alone. Still, Over time, the interference fringes bloom with surgical precision. Each solitary electron appears to consult a silent, unseen crowd of its own possibilities before deciding where to land. Confusion ripples outward. If electrons behaved purely as waves, the pattern would make sense, but waves arrive as continuous ripples, not single, staccato flashes. If they behaved purely as particles, the fringes would vanish, leaving two simple piles. Instead, the screen records a truth stranger than either picture alone. Every electron is both, or rather it is something deeper in amplitude of potential paths, collapsing into a single dot only at the instant of detection. Colleagues propose hidden dirt on the slits, stray electric fields, faulty screens. One by one, those excuses die. The result endures across light: electrons, neutrons, even giant carbon-60 molecules, each containing 720 nucleons. Scale up the mass 1,000-fold, and quantum rules still refuse to yield. The universe seems to insist. Superposition. Multiple realities coexisting is not a laboratory fluke. It is the opening move of every interaction, from starlight striking your retina to atoms forging life's first proteins. And so the double-slit reveals its ultimate lesson. Reality holds its breath in overlapping drafts, till observation pins a single version to the page. If a lone electron can weave two paths at once, perhaps the trick is simple ignorance. So physicists add tiny detectors, microscopic flashbulbs, just behind each slit. Their mission: announce, unambiguously, left or right. The moment the detectors click, the interference fringes vanish. The screen fills with two mundane blobs, as if the electron suddenly remembers it must behave like a classical pellet. But watch closely. The detectors are whispered quiet, drawing almost no energy. They don't jostle the electron the way a hammer startles a bell. Instead, their mere availability to record which path information erases the wave of possibilities. Observation isn't a nudge, it's a negotiation. Once the universe delivers the answer, it deletes every alternative draft. Turn the detectors off, and the fringes return like ghost handwriting under lemon juice. Reality, it seems, is not filmed in secret and replayed later. It is written in the act of asking. To make sense of this, physicists embrace a radical rewrite. Particles do not carry precise trajectories until measured. Instead, each possesses a wave function, a mathematical melody that assigns an amplitude to every possible path. Add two amplitudes, and they can reinforce or cancel, just like overlapping ripples on a pond. Yet the wave function is not a material ripple. It lives in abstract space, predicting probabilities, not certainties. Only when a detector fires does one possibility crystallize, its likelihood given by the square of the amplitude. Born's rule. This shift reframes reality. The universe is less a clockwork and more a vast decision tree. Branches weighted by probability until observation prunes all but one. Between emission and detection, the electron isn't smeared matter, it is potential, an ensemble of futures humming in superposition, and this isn't limited to subatomic realms. In photosynthesis, excitons explore many molecular routes simultaneously, choosing the most efficient path to drive life's energy economy. Your phone's semiconductor logic relies on electron waves tunneling through barriers no classical object could cross. The double-slit, then, is not a curiosity, it's a Rosetta Stone. It teaches us to read the language of amplitudes, interference, and collapse, a dialect spoken by every atom and echoed in every ray of starlight. The skeptic's last refuge is scale. Perhaps superposition only rules the realm of the truly tiny. So experimenters upsize the test subjects. First come neutrons, 2,000 times heavier than electrons, still drawing crisp interference fringes. Then atoms, clusters of protons, neutrons, electrons marching together as a single quantum wave. The patterns persist. In 1999, researchers at Vienna load a beam with football-sized cages of 60 carbon atoms, buckyballs. Each molecule is a miniature geodesic dome, 1 billion times heavier than a photon. One by one, they glide through to nanoscopic slits. Hours later, the detector screen blooms with a familiar zebra-striped signature. Even this molecular giant travels every available path at once until forced to decide. Today, the record stands at organic compounds of hundreds of atoms. Each behaves like a programmable probability cloud. The boundary between quantum and classical is not particle size, it is isolation. Shield a system from stray gas molecules, thermal jostling, and starlight, and superposition scales upward with eerie ease. The lesson is unsettling. Your desk, your heartbeat, the moon herself would exhibit the same interference. Were they not incessantly measured by trillions of environmental collisions? Quantum isn't small, it is simply shy, vanishing when the world looks on too closely. What if reality could be cornered by timing? Physicist John Wheeler proposes a twist. Decide after a particle passes the slits whether to reveal which path it took. In the laboratory, photons enter a Mach-Zehnder interferometer. 2 arms, 2 mirrors. At the last instant, a movable beam splitter either recombines the paths, inviting interference, or removes the possibility, recording which route. Astonishingly, the photon's earlier behavior conforms to the future choice. If the splitter is present, interference appears, as though the particle always traveled both routes. Remove it, and the photon seems to have picked a single arm all along. The decision made nanoseconds late rewrites the past description without violating causality. Probabilities were never locked until information became available. Push further. The quantum eraser stores which path data on an entangled partner photon. Erase that information after detection, and the interference fringes revive in retroactive clarity. It is not that events travel backward in time, but that nature withholds commitment until every shard of potential knowledge is settled. These delayed choice experiments close the loophole of hidden trajectories. The universe does not keep a secret ledger of definite histories. Instead, events exist as overlapping drafts that finalize only when the web of information, present and potential, snaps shut. Close the lab door, and the pattern doesn't stay behind. It follows you into every technology, every cell, every star. Your laptop's processor works only because electron waves interfere inside silicon, tunneling through barriers that classical charge could never cross. Lasers exploit coherent superpositions of photon states. MRI scanners read quantum spin, echoes in the hydrogen of your body. Look to biology. In the leaf of a fern, excitons born from sunlight explore countless molecular routes simultaneously. Then interfere to select the most efficient path. Nature's quantum optimization routine. In birds, entangled electron pairs inside cryptogram proteins may let them sense Earth's magnetic field, guiding migrations that paint half the globe in wings. Even the night sky carries quantum fingerprints. Fusion in the sun depends on proton tunneling. Without it, our star would be a cold orb of hydrogen, cosmic structure itself galaxies, clusters. The web of dark matter originated from quantum jitters in the infant universe, later stretched by inflation. Thus, the double slit is not a parlor trick. It is a master key revealing that probability amplitudes underpin chemistry, life, and cosmology. Quantum mechanics is not an exotic overlay. It is the operating code beneath the desktop of classical appearances. Understanding that code is how we build qubits, fault-tolerant sensors, and perhaps one day warp drives of calculation rather than motion. Interference tells us nature holds many options in reserve. But it doesn't explain why those options can never be sharpened into perfect certainty. Measure a particle's position with finer and finer resolution, and its momentum begins to blur. Pin down its energy, and the timing of events smears outward. These trade-offs are not experimental clumsiness. They're woven into the fabric of existence. In Part 2, we meet Heisenberg's uncertainty principle. Often misread as a nuisance, but actually is a pillar that prevents atoms from imploding and sets the minimum hum of every quantum field. We will descend into zero-point energy, watch vacuum fluctuations pop particles into being, and see how uncertainty rescues stars from gravitational collapse, while setting the very noise floor of reality. The double slit showed us that possibilities interfere. Uncertainty will show us why possibilities must remain fuzzy until the very act of being is complete. Together they declare, the quantum is not optional, it is compulsory, creative, and inescapable. Join me as we turn the page from shimmering fringes to the restless heartbeat of indeterminacy itself. For centuries, science worshipped a clockwork dream. If you knew every particle's position and momentum proclaimed Laplace's demon, You could predict the cosmos from the flutter of a moth to the drift of galaxies past, present, and future, etched in perfect script. Then came Werner Heisenberg, holding a lantern to the tiniest shadows. He found that nature does not allow both gifts at once. Pin down a particle's location more precisely than the width of an atom, and its momentum blurs like ink in water. Sharpen the momentum, and the particle's whereabouts dissolve into probability mist. It isn't technological clumsiness, it is the universe's handwriting. A limit woven not by measurement tools, but by existence itself. Strip away every vibration, cool an atom to a whisper above absolute zero. And still the product of its uncertainties refuses to shrink beyond that boundary. Determinism cracks not from chaos, but from a deeper order that trades perfection in one realm for ambiguity in another. The cosmos will divulge secrets, but never all of them at once. To glimpse the reason, picture a single violin note stretched into silence. The purer the pitch, the longer it rings. Shorten the burst, and overtones bloom. Mathematicians call this Fourier's law. Confining a wave in one domain spreads it in another. Every particle is a wave packet, a pulse of possibilities. Squeeze its position, tighten the spatial envelope, and the momentum spectrum widens, a shimmering fan of wavelengths. Let the wave wander broad and gentle, and its momentum sharpens like a spear. No tinkering circumvents the trade-off, because the particle is the wave, localization is distortion. Fire electrons through a nanoslit just billionths of a meter wide, and their diffraction pattern splays across the screen, proving their momentum uncertainty has ballooned. Do the same with fullerene molecules heavier than 7,000 hydrogen atoms, and the pattern returns grand but obedient. Even buckyballs cannot dodge the wave rule. Photons, neutrons, atoms, viruses, however massive, they carry a quantum heartbeat that insists precision be paid for in complementary coin. Uncertainty is not a veil over hidden facts. It is the rhythm by which waves exist in space and time. The inevitable soundtrack of a universe that refuses absolute stillness or pinpoint certainty. Cool a pendulum, and it slows. Cool it further, and it stills. Classical intuition says perfect calm awaits at absolute zero. Quantum logic refuses. Even when thermal jitters are bled away, every atom, photon, and field retains a faint, restless tremor, zero-point energy. Picture an electron bound to an atomic nucleus. If position and momentum could both fall to zero, the uncertainty product would break Heisenberg's limit. Instead, the electron hovers in a whisper-wide orbital, a standing wave that never fully settles. The residual motion keeps atoms from collapsing and gives matter its size. Zero-point energy escapes the microscopic too. Chill liquid helium to a fraction of a degree above absolute zero, and it refuses to freeze. The atom's quantum jiggle overrides the lattice that would lock them into ice. Bring two uncharged metal plates a hair's breadth apart in vacuum. And vacuum fluctuations push them together, the Casimir effect. Measurable proof that empty space seethes with invisible modes. Far above your head, the same vacuum seeds cosmic microwave background ripples. In your laptop, it sets the noise floor for every transistor. Motion that never stops may sound like celestial nuisance, but it is the crackle that keeps stars aflame, chemistry alive, and the fabric of space humming with potential. Position and momentum share one trade-off. Energy and time share another. Borrow a tiny packet of energy, and the universe allows the loan so long as it's returned rapidly. Borrow more, and the repayment deadline shrinks. These fleeting overdrafts manifest as virtual particles, ripples that flicker into being, then fade before detectors can flag them as real. Between two electrons, virtual photons zip back and forth, mediating electric repulsion. Inside a bar magnet, a storm of virtual quanta binds domains into north and south. No conservation laws are broken. The energy ledger balances when T expires. At the edge of a black hole horizon, quantum loans become cosmic withdrawals. A virtual particle pair pops from vacuum. Gravity yanks one partner past the event horizon, while its twin escapes as Hawking radiation. The black hole pays the debt with its own mass, evaporating atom by atom over eons. Even radioactive decay clocks the universe by this principle. The shorter-lived and excited nucleus. the broader its energy spread, imprinting uncertainty onto every gamma ray it emits. Our finest lasers, atomic clocks, and PET scanners all ride this line with. Energy time uncertainty is not a loophole. It is the gears of interaction, the fleeting handshake that lets forces work. Black holes glow and random decay inject genuine unpredictability into the cosmic script. Imagine shrinking an electron's orbit until it almost kisses the nucleus. Electrostatic attraction says closer, closer, promising lower potential energy with every step. But Heisenberg stands guard. Tighten the electron's position too much and its momentum uncertainty. Its quantum pressure soars, adding kinetic energy that counters the Coulomb pull. Equilibrium emerges where these two forces balance, carving out the Bohr radius and every atomic shell beyond. This tension between attraction and quantum pushback builds the scaffolding of chemistry. Hydrogen's solitary electron spreads just enough to create gentle, covalent bonds. Heavier atoms, flush with electrons and Pauli exclusion, arrange layered orbitals that set the periodic table's rhythm. Strip uncertainty from nature and electrons spiral inward. Atoms collapse into pinprick nuclei. Matter as we know it ceases. Your desk, your bones, the air. Everything solid owes solidity to the restless blur, encoded in Heisenberg uncertainty principle. Even white dwarf stars rely on this principle. Squeeze stellar ash under gravity, and degenerate electrons push back, suspending a sun's mass on a sphere no larger than Earth. Quantum fuzziness is not decorative. It is structural steel, holding up atoms, planets, and the quiet weight of night. 14 billion years ago, the universe was a subatomic ember, fields vibrating with quantum uncertainty. During cosmic inflation, that ember ballooned faster than light's own pursuit, stretching microscopic fluctuations into macroscopic ripples, minuscule overdensities that would later attract dark matter, gas, and eventually galaxies. Today, we see their fossil imprint in the cosmic microwave background, a modeled tapestry of one part in 100,000 temperature bumps. Each bump a quantum hiccup amplified across intergalactic emptiness. Point a radio telescope at the sky, and you're reading the static of Heisenberg's jitter grid, 100,000 light-years wide. Zoom further. Gravitational wave detectors strain to hear primordial hums, stochastic ripples perhaps birthed by the same quantum seeds. The large-scale cosmic web, with its filaments and voids, is a three-dimensional echo of vacuum noise frozen on scales larger than clusters of galaxies. Thus, uncertainty is not confined to atoms. It sculpts the scaffolding of the cosmos. Every spiral galaxy, every star nursery, even the supercluster that hosts our Milky Way, owes its existence to random quantum flickers stretched to celestial grandeur. The night sky is a mural painted by probability, its brushstrokes chosen in the first trillionth of a second after time began. Physicists are stubborn. They turn limits into laboratories, shrink a beam of single photons until its waist is narrower than a bacterium, and watch the diffraction halo bloom. Direct proof that the uncertainty in position and the uncertainty in momentum refuse divorce. Trap a single calcium ion in an electromagnetic cage, cool it with laser light, and measure its position spread. Never zero. Always the ground state wiggle set by zero-point motion. Energy-time trade-offs leave fingerprints too. Excite sodium atoms with a nanosecond laser pulse, and their spectral lines broaden precisely, as Heisenberg uncertainty principle predicts. An atomic heartbeat engraved in color. Particle physicists push further. Unstable pions born in accelerators live trillionths of a second. And their rest mass smear follows the same rule, confirming that nature tallies every loan with quantum bookkeeping. Squeezelight labs flip the script. They narrow photon number uncertainty at the cost of phase fuzz, beating the shot noise limit in gravitational wave detectors. LIGO's record-breaking sensitivity to spacetime ripples depends on this engineered give and take, turning Heisenberg from barrier into amplifier. Each experiment, photon halo, atomic line width, quantum squeeze-all whisper the same refrain. Uncertainty isn't an error bar we hope to erase. It is a constant carved into the grain of reality, and with clever tools we can bend, but never break. It's arithmetic. Scan your fingertip with an MRI, and you exploit proton spins dancing to quantum tune, their resonance width fixed by the uncertainty principle for energy and time. Probe a single atom with a scanning tunneling microscope. Electrons tunnel, because position is fuzzy and energy momentarily borrowed. Inside GPS satellites, atomic clocks count microwave ticks of cesium. Clock's ultimate accuracy is shackled by energy-time uncertainty, yet honed by decades of squeezing noise toward that limit. Miss a few nanoseconds and your phone maps you to the wrong street. Cryptographers harvest radioactive decay or photon arrival jitter to generate randomness no algorithm can predict. Quantum key distribution uses the impossibility of simultaneously knowing polarization and phase to catch eavesdroppers. Steal info. Stored in uncertainty, get caught. Emerging quantum sensors read changes in magnetic or gravitational fields, so slight they would vanish beneath classical noise. But balanced atop Heisenberg's edge, they detect submarine wakes, underground voids, perhaps even dark matter waves. All rely on trading precision in one variable for ignorance in another, dancing with the limit rather than fighting it. Without uncertainty, we lose lasers, semiconductors, PET scans, and the encryption that shields every online handshake. The fuzz is not a flaw. It is the fertile ground where innovation takes root. Uncertainty tells us that nature refuses perfect focus, yet it does not show the full spectacle of possibility. To see that, we must let systems hold many truths at once, interfering like overlapping melodies before the final note sounds. In Part 3, Superposition. Reality in draft mode. We will watch quantum states layer like transparent pages, discover why Schrödinger's cat was always more parable than paradox, and learn how chlorophyll quantum computers and tunneling enzymes wield superposition as everyday toolkit, where uncertainty sets the blur. Superposition paints the multicolored draft. Together they reveal that the quantum is not a quirky footnote to classical chapters. It is the manuscript still wet with ink. Beneath every story the universe will ever tell. Imagine writing a sentence where every verb, noun, and adjective exists in multiple choices at once. An invisible stack of drafts. In quantum mechanics, that sentence is the wave function. It doesn't declare what is, but lists everything that could be, weighted by complex amplitudes. Numbers that carry both size and rhythm. Before measurement, an electron near an atom is not here or there. It is a chorus of positions humming in phase, a spectrum of momenta keeping the beat. Dirac captured this chorus in a simple symbol, psi, a state vector living in Hilbert space. Add two vectors and you don't pick one outcome, you superpose them, creating a pattern where peaks and troughs can later interfere. When you measure, the chorus quiets, leaving a soloist one definite note. But the music we call reality depends on the whole score written beforehand. Collapse is merely the final chord we hear. Superposition, then, is not indecision. It is the universe running parallel drafts, each a viable future. Measurement is the editorial moment when all but one draft are filed away. Invisible, yet indispensable to the story that remains. To feel superposition's power, shrink yourself to ride a single photon through a Mach-Zehnder interferometer. First, a beam splitter sends half your amplitude down path A, half down path B. Mirrors return both streams to a second splitter that decides where you exit. Classical reasoning says 50 to 50. Quantum reasoning adds amplitudes. If the paths are equal length, the peaks align toward detector 1 and cancel toward detector 2. 100 photons later, detector 1 has all the clicks. Detector 2 sits ignored. Now a human hand inserts a tiny glass plate in path B, delaying its phase by half a wavelength. Suddenly, detector 1 falls silent, and detector 2 lights up every time. Nothing touched the photon halfway. Only the relative phase, the rhythm between the drafts, was tweaked, steering the result. The photon did not choose path A or B. It traveled both, letting its split possibilities interfere to guide a deterministic outcome no classical particle could mimic. Engineers exploit this self-interference in atomic clocks, fiber gyroscopes, and gravitational wave observatories. Quantum computers will extend the idea, route qubits through computational mazes where wrong answers cancel and right answers amplify. Interference turns potential into power. information distilled from waves that explored every corridor simultaneously. Erwin Schrödinger never intended his boxed cat to haunt popular culture. He meant it as a cautionary tale, link a quantum event, a single radioactive decay to a macroscopic trigger. And logic seems to stall. Before observation, the nucleus is both decayed and intact, the vial both intact and shattered, the cat both dead and alive. In labs today, we've replaced cats with resonators and microwave cavities. Physicists at Yale coax a single superconducting circuit into carrying two opposite currents simultaneously, clockwise and counterclockwise. Then entangle that loop with a microwave photon field holding cat states of tens of energy quanta at once. Elsewhere, silicon ionospheres are magnetically levitated, center of mass placed into two spatial locations, separated by more than their own diameter. Proof that superposition can cradle billions of atoms. Why don't we witness living felines in dual fates? Because every breath, photon, and thermal vibration acts as a relentless eavesdropper. In microseconds, the environment records cat status, collapsing the draft. Decoherence, not size alone, partitions quantum possibilities from classical outcomes. The moment a system leaks which state information faster than we can isolate it, the illusion of singular reality congeals. Schrödinger's lesson endures. The boundary between weird and ordinary is not mass, but our inability to keep secrets from the universe. A classical bit is a switch, 0 or 1. A qubit is a compass needle on the Bloch sphere, free to point anywhere in a continuum of 0 and 1 combinations. The magic emerges when you wire many qubits together. 10 qubits hold 2 to the power 10 or 1024 parallel drafts. 300 qubits exceed the number of atoms in the observable universe. Physicists craft qubits from superconducting transmans, trapped high in strings, silicon spin dots, and single photons in waveguides. In each, superposition is stabilized just long enough to choreograph interference. Take Grover's algorithm. Start with a uniform superposition of all database entries. Apply operations that invert amplitudes of wrong answers, and let interference cancel most paths while amplifying the target state. For operations on 2-qubit superpositions can outpace millions of classical evaluations. Early quantum processors already simulate molecular orbitals that break classical scaling. Variational algorithms tweak qubit superpositions to predict catalyst energies or optimize battery materials. Behind the scenes, error-correcting surface codes and cat code qubits weave redundancy, fighting decoherence by spreading one logical state across dozens of physical qubits, embracing uncertainty rather than denying it. In essence, quantum computing is disciplined superposition. The machine explores every corridor of a maze simultaneously, then interferes paths so only the exit glows bright. The more stable the drafts, the faster the glow reveals answers no classical light can reach. Long before physicists chilled qubits in dilution refrigerators, photosynthetic bacteria were steering superpositions through tangled protein mazes. When a photon strikes a chlorophyll cluster, it spawns an exciton, a mobile packet of energy that must find the chemical reaction center. Lab lasers reveal quantum beats lasting hundreds of femtoseconds as the exciton explores every molecular hop simultaneously, then interferes to choose the quickest path. Migratory robins may navigate by a different quantum whisper. Inside their retinal cryptochrons, a pair of entangled electrons begins in superposition, spin-aligned and spin-opposed. Earth's weak magnetic field tilts the balance, altering downstream chemistry that the bird perceives as visual cues. Break entanglement with oscillating radio waves and the avian compass falters, suggesting quantum drafts guide journeys that span continents. Even your nose might rely on molecular tunneling. Some theories propose that odor receptors detect vibrational spectra via electrons, sampling superposed pathways through scent molecules. The jury is still out, but the pattern is clear. Life learned to keep delicate quantum books long before humans built spectrometers. Where energy is scarce and efficiency vital, superposition becomes an evolutionary tool, quietly optimizing processes at the edge of thermal noise. In a solid-state ring only millimeters wide, a squid loop can host currents flowing clockwise and anti-clockwise at the same instant. demonstrated by interference fringes in magnetic flux. That's billions of Cooper-paired electrons sharing two contradictory realities. Researchers now eye even bigger prey. Levitated silica beads, 100 nanometers across, are cooled near their motional ground state. Plans call for launching them into free fall aboard sounding rockets or space platforms, then splitting their wave functions by pulsed magnetic gradients. If interference fringes appear, we will have placed objects visible under an optical microscope into spatial superposition. Some proposals push towards kilogram-scale mirrors inside gravitational wave detectors. By squeezing quantum noise and isolating thermal vibrations, physicists hope to coax these mirrors, each containing 10 to the power 25 atoms, into mutually exclusive displacement states differing by less than a proton's width. Such feats will probe whether gravity itself respects quantum drafts or enforces collapse, a question entwined with theories from Penrose's objective reduction to string theory fuzzballs. Each increment in mass tightens decoherence's grip, yet advances in cryogenics. Vibration isolation and vacuum technology keep moving the line. The dream is audacious. Watch the everyday world slip its classical mask, only for microseconds, and glimpse superposition written in objects we can almost touch. Why don't we witness coffee mugs orbiting every point on the table at once? Because the universe is an unforgiving gossip. The moment a quantum system interacts with stray photons, phonons, or air molecules, information about its draft leaks outward, entangling with trillions of environmental degrees of freedom. This decoherence shreds phase relationships that allow interference, converting elegant superpositions into statistical mixtures. Certain pointer states, robust configurations like a chair's location, survive because they imprint minimal ambiguity on the environment. Decoherence selects these states through environment-induced superselection. It's called Ein selection, giving rise to the classical world we trust. Quantum engineers fight back with error-correcting codes, spread a logical qubit across many physical qubits, so that local noise can be detected and reversed without measuring the delicate superposition itself. Cat code resonators encode information in superpositions of millions of photons. Surface codes tile superconducting qubits into two-dimensional grids that tolerate thousands of defects. Each scheme buys coherence time by quarantining information leaks. An arms race between isolation and the universe's incessant curiosity. Atom interferometers drop ultra-cold rubidium clouds in Earth's gravity, splitting and recombining their wave functions to measure tiny phase shifts. The result? Portable gravimeters that can map buried caverns or monitor magma chambers beneath restless volcanoes. Quantum lithography uses entangled photon superpositions to beat the Rayleigh limit. Sculpting semiconductor features smaller than classical optics permit. LiDAR systems under development exploit photon number phase trade-offs, generating ghost images that reveal objects with dramatically fewer detected photons. Ideal for covert surveillance or low-dose medical scans. In chemistry labs, photonic boson sampling devices tap multipath interference to model molecular vibrational spectra exponentially faster than classical Monte Carlo methods, hinting at breakthroughs in drug design and carbon capture catalysts. Financial firms eye quantum annealing superpositions to navigate rugged optimization landscapes, from portfolio balancing to supply chain logistics. Down the road, quantum radar concepts propose entangling, outgoing, and retained microwave photons. By comparing the returning echoes with their stored twins, they promise target detection that pierces classical jamming. Each application is a testament to harnessing drafts, setting up conditions where wrong answers erase themselves and the right one rings like a bell. A lone quantum system already carries parallel possibilities. Stitch two together, and potential multiplies non-locally. Entanglement allows particles oceans apart to share a single composite draft. Alter one and the other's probabilities adjust instantly, though information remains light-bound. Next, in Part 4, Entanglement. When here knows there. We will follow photons through Bell tests that demolish hidden variable hopes. Watch quantum networks teleport qubits across continents, and explore how space-time geometry may itself emerge from webs of entanglement. Superposition showed us individual uncertainty blooming into power. Entanglement will reveal cooperation without communication, correlations deeper than any classical loom can weave. Together, They underscore the documentary's central claim. The quantum is not optional. It is the stage, the script, and the spotlight of reality itself. In 1935, three minds, Einstein, Podolsky, and Rosen, sat uneasily at the edge of quantum dawn. They proposed a thought experiment meant to expose an incompleteness in Schrödinger's strange new map. Two particles spring from a single source, momentum balanced like skaters pushing apart on frictionless ice. Measure one far away, and, in that instant, you deduce the other's momentum without touching it. Einstein called the implied connection spooky action at a distance. Either information travels faster than light, violating relativity, or quantum mechanics fails to tell the whole story. He wagered on hidden variables, secret settings carried at birth, quietly scripting each particle's reply to future questions. If such variables exist, correlations between distant results can never exceed a certain classical ceiling. The EPR paper was more than criticism, it was a gauntlet. Either reveal the concealed gears of reality, or accept that measurement here can instantaneously reshape potential there despite oceans of vacuum between. For decades, the question lingered, an unresolved debate carved into footnotes until a Northern Irish physicist converted philosophy into an experimentally testable inequality. John Bell, tinkering after hours at CERN in 1964, translated EPR's debate into a game of statistics. Picture Alice and Bob at opposite ends of the galaxy, each with a detector that can be set to one of two angles. They measure entangled photons and record outcomes as bits, +1 or -1. Classical hidden variables predict that, averaged over many runs. Certain combinations of correlations now wrapped into the CHSH inequality can rise no higher than 2. Quantum mechanics, in contrast, forecasts a larger wave-like correlation. Multiply Alice's and Bob's bits, add and subtract in the right pattern, and you obtain 2 square roots of 2 approximately equals 2.8 to 8, a clear breach of the classical ceiling. Crucially, this prediction does not require faster-than-light signaling. The spooky link lives in the shared quantum draft written before the particles parted. Bell's inequality offered experimenters a lights-on scoreboard. Violate the bound and hidden variable realism falls. Early tests in the 1970s suggested quantum victory but left loopholes such as detectors too slow and settings chosen in advance. The stage was set for a new generation of experiments that would fire photons, flip random coins at nanosecond speed, and finally decide whether the universe keeps private ledgers or truly lets distant events share one inseparable story. 2015, 2 labs, one in Delft, another split between Vienna and the Canary Islands. They armed themselves with the fastest optics and the coldest crystals on Earth. In Delft, Diamond Lattice hosts single nitrogen vacancy centers. Each spin is entangled with a photon that races through optical fiber to a central station. In Spain, entangled photons leap from La Palma's mountain observatory across 143 kilometers of open sky to Tenerife. Random number generators, fed by quantum shot noise, choose detector settings after the particles are already in flight. High-efficiency superconducting sensors close the detection loophole. Spaced-out stations ensure choices are space-like separated, closing the locality loophole. When the counts are tallied, the CHSH score lands above 2.4. Decisively beyond the classical cap of 2, exactly where quantum theory predicts. Hidden variable realism, at least of the local kind, is out. No secret script, no subliminal handshake can explain statistics that demand a single shared draft across light years of potential separation. Einstein's worry remains. Spooky? Yes. But the universe votes with the data. Entanglement is woven into its fabric, and any deeper theory must carry the same non-local heartbeat. Entanglement does more than violate inequalities. It forms the backbone of quantum teleportation, transferring a state while leaving the particle behind. Alice and Bob share an entangled pair. Alice performs a joint Bell state measurement on her half and an unknown qubit she wishes to send. The act entangles history, collapsing Bob's distant qubit into a state related to the original by a known rotation. 2 classical bits race along fiber or satellite link. Bob applies the correcting twist, and the quantum message is restored. Original, destroyed, copy, reborn. No faster-than-light courier required. The first demonstration, 1997, Innsbruck, sent photon polarizations across a few meters. 2 decades later, China's Mishia satellite teleported qubits between ground stations that are 1,200 kilometers apart through the shimmer of the upper atmosphere. In labs, ions, NV centers, and superconducting circuits now teleport states between memory nodes. The essential move for a quantum repeater, and hence stretching fragile entanglement across continents, teleportation shifts focus from moving matter to moving information, hinting at networks where quantum keys distribute unbreakable security. Clock arrays sync with attosecond precision, and distant telescopes merge into planet-sized interferometers. All because pairs of particles once entangled behave like two ends of a sentence that cannot be split without losing meaning, no matter the gulf between. Think of a future internet whose backbone isn't copper or glass, but shared quantum drafts. In this network, entangled photon pairs are generated at central factories, buffered in quantum memories, cold atoms, rare earth crystals, superconducting resonators, then swapped node to node. Each swap entangles memories farther apart, stitching kilometers, then continents, into one non-classical web. Such a web does more than move qubits. Two widely separated atomic clocks, entangled rather than merely synced, can average away local noise. Ticking in tandem with precision, unattainable by classical links, long baseline telescopes, fed entangled photons, could interfere starlight collected on opposite sides of Earth, yielding images as sharp as a single mirror the planet's width. Entanglement also sharpens sensors. A ring of interferometers seeded with squeezed, entangled light already underpins the record sensitivity of LIGO and Virgo. Next-gen detectors dream of spotting primordial gravitational waves or the gentle murmur of dark matter fields. In biology labs, entangled two-photon microscopy reduces tissue damage while boosting contrast, letting researchers watch neuron circuits fire without frying delicate cells. Every application treats entanglement as currency difficult to mint, priceless once spent, and subject to strict accounting. Lose a single photon, and the ledger crumbles. Hence the race to build memories, repeaters, and error-resilient protocols before decoherence can steal the coins. Entanglement comes with a jealous streak. If two qubits share maximal correlations, no third system can possess comparable knowledge about them, a rule called monogamy of entanglement. This exclusivity forms the bedrock of device-independent quantum key distribution. Alice and Bob perform random Bell test measurements on shared entangled pairs. If their statistics violate Bell inequalities by a healthy margin, physics itself certifies that no eavesdropper could hold a copy of their key. Any attempt to tap the line would sap correlations, lowering the score and sounding an alarm. Unlike classical cryptography, security here depends not on computational hardness, but on the impossibility of cloning entanglement. Monogamy also powers randomness expansion. Generate a short seed of trusted random bits. Feed them into entanglement-based games that Bell violate. And you unlock long strings of certified unpredictable numbers critical for secure lotteries, simulations, and national security protocols. The same principle limits quantum networks. Entangled resources are precious because they cannot be freely shared. Engineers therefore invent entanglement distillation, purifying multiple noisy pairs into fewer, higher quality links through local operations and classical chat. In every protocol, the jealous nature of quantum correlation is both obstacle and shield. Constraining architectures, even as it guarantees privacy no classical system can match. Entanglement is not confined to lonely pairs. In condensed matter jungles, it links trillions of electrons into collective personalities. Peel back a sheet of graphene cooled near absolute zero, and you'll find currents twirling in fractional quantum Hall states, which are topological orders where anion quasi-particles carry fractions of an electron's charge. Their behavior is scripted by webs of multi-body entanglement that wrap around holes in the material, like invisible laces, immune to local snags. Physicists quantify this hidden order with entanglement entropy. In ordinary matter, entropy scales with volume. In exotic phases, it hugs the area of a boundary, revealing long-range quantum stitching beneath. Tweak a parameter, magnetic field, disorder. Measurement rate and the system can undergo an entanglement phase transition. Not a change in symmetry or density, but in how information flows. Recent quantum circuit experiments have observed a critical point where random measurements sever enough links to tear a highly entangled state into disconnected islands. A novel kind of quantum percolation. Such many-body drafts might fuel fault-tolerant qubits built from non-abelian ions, where braiding world lines performs logic gates immune to microscopic noise. If successful, quantum computation will rely not on isolated pairs, but on seas of entanglement, arranged like intricate origami, robust, global, and strangely beautiful. What if the threads binding particles also stitch the cosmos? The ER equals EPR conjecture, proposed by Moldacena and Susskind, suggests that every entangled pair is connected by a microscopic, non-traversable wormhole. Stretch that thought. We've vast carpets of entanglement, and space-time geometry itself could emerge from the pattern. Tensor network models like Mera build holographic universes where each link is an entangled bond. Cut enough bonds and the simulated space pinches off, mimicking black hole horizons. In anti-de Sitter spacetime, the Rudikai-Yanagi formula equates the area of a minimal surface to entanglement entropy, turning geometry into bookkeeping for quantum information. Recent island calculations describing Hawking radiation entanglement recover the page curve, hinting that black holes do not destroy information. They release it through correlations woven across event horizons. Tabletop experiments with superconducting qubits have even simulated toy wormholes, teleporting quantum states via entanglement-assisted circuits that mirror gravitational dynamics in one spatial dimension. These ideas remain conjectural, but the takeaway is profound. Space-time might not be a stage, but a tapestry whose threads are entanglement itself. Alter the pattern, and geometry warps, sever it, and space could crumble like a pulled sweater. Entanglement is fragile in the wild. Stray photons, vibrating lattice, cosmic rays. Each interaction siphons coherence, handing information to the environment and converting quantum poetry into classical prose. This is decoherence, the same relentless leak that saved Schrodinger's cat from eternal limbo. Quantum engineers respond with entanglement distillation, compressing many noisy pairs into fewer but purer links, and with error-correcting architectures that spread a logical qubit across hundreds of physical ones. Surface codes form two-dimensional quilts where any local tier can be sewn shut. Emerging LDPC codes promise similar protection with fewer stitches, yet there is balance. Absolute isolation kills usefulness. Quantum sensors need just enough coupling to read the world without drowning in it. The art is to negotiate a ceasefire in the tug of war, keep the drafts coherent long enough to compute, sense or communicate, then let them collapse when their story is told. Entanglement reveals a universe knitted together by invisible threads, but daily experience hides the weave. The culprit is noise, sunlight, air, thermal jiggle, constantly measuring, constantly collapsing, erecting the sturdy walls of classical cause and effect. Part 5, Decoherence. Why we don't notice will follow that noise, showing how environmental observers sculpt pointer states, why macroscopic irreversibility blooms from reversible equations, and how life leverages just enough quantum subtlety before surrendering to thermodynamic tide. We will explore quantum Darwinism, meet quantum error correctors, fighting entropy, and see how the same leaks that steal coherence give rise to the arrow of time. Entanglement has shown us the hidden webs. Decoherence will explain why those webs rarely sparkle in daylight, yet never fully disappear. Watch a film of two billiard balls colliding. Run the footage backward, and the scene feels perfectly plausible. The equations guiding that impact. Schrodinger's wave law, Maxwell's light waves, Newton's gravity are time-symmetric. They do not prefer yesterday or tomorrow. Yet outside the chalked felt, glasses shatter, but never reassemble. Smoke escapes, but never retreats, and human memories grow in one direction only. Where does irreversibility arise if the bedrock is reversible? The answer hides in an ocean of overlooked degrees of freedom, trillions of air molecules, stray photons, lattice vibrations. Every macroscopic event leaks quantum information into this environment. Phase relationships, those delicate alignments that let superpositions interfere, spread outward at nearly the speed of light, too fine-grained ever to be coaxed back. What looks like collapse is entanglement gone cosmically diffuse. Thus, the arrow of time is not carved by fundamental laws, but by practical impossibility. We cannot gather and reverse the countless whispers our actions shout into the world. Decoherence turns microscopic reversibility into everyday one-way traffic. Eggs that fall but do not uncrack. Stars that radiate but never reignite their spent photons. Imagine a coin balanced on its edge inside a perfect vacuum. Is it heads, tails, or both? In isolation, quantum rules would allow a superposed answer, but our universe refuses isolation. A single microwave photon brushing past can learn the coin's tilt. An infrared vibration in the table records a soft echo. Each interaction copies a fragment of which side into countless environmental bits. This copying is decoherence in action. System-environment entanglement that smears phase relations beyond retrieval. In a laboratory, physicists can watch it happen. Send C60 molecules through twin slits and gradually raise the ambient gas pressure. At a few collisions per millisecond, interference stripes fade like morning mist. The molecules are still in superposition. The scattered gas now carries the path information, rendering fringes invisible. The environment is an omnipresent camera with no off switch, sculpting reality by relentless surveillance. Classical states like definite positions and robust magnetic domains survive because they broadcast distinct, redundant signals that many observers can sample without disturbing the source. Quantum drafts that lack this redundancy dissolve almost instantly. In other words, the world we perceive is the subset of quantum possibilities that can keep a secret from nothing and no one. Not every quantum draft is doomed. Certain configurations, an atom's location, a dust mote's trajectory, a planet's orbit, proved remarkably stout. Wojciech Zurek christened them pointer states, patterns that survive environmental scrutiny because they imprint clear, consistent records while shedding minimal phase ambiguity. The environment, acting like a cosmic publisher, copies those records into trillions of photons, phonons, and air molecules. This redundancy gives rise to quantum Darwinism. Just as biological traits spread by replication, it's only quantum states that can broadcast many identical templates become objectively real. Multiple observers sampling different pieces of the environment, reflected light here, scattered sound there, will all agree on the pointer state without ever disturbing it. Our shared classical world is thus the fittest survivor of an endless competition for informational airtime. Laboratories now film this survival contest. In Vienna, fullerene molecules traverse a 100 nanometer grating. Lower the background pressure and interference fringes gleam. Bleed a puff of argon gas and collisions erase stripes molecule by molecule. At MIT, superconducting qubits lose coherence in microseconds as stray infrared photons slip through shielding. Measurable on oscilloscope traces that sag from coherent oscillation to noisy plateau. From femtosecond electron diffraction to second-long ion-trapped clock qubits. Every platform maps a decay curve. Gaussian at first, exponential later, charting how swiftly the environment steals phase information. Collapse is not an event, but a diffusion, a bloom of entanglement radiating outward faster than we could hope to reverse. Because entanglement spreads one way, entropy must rise. Each micromeasurement adds bits of information the universe must keep track of, enlarging the environmental Hilbert space. Reversing that growth would demand recollecting every photon your breakfast cereal emitted into the kitchen walls. Possible in principle, absurd in practice. Thus Loschmidt's paradox evaporates. Microscopic reversibility coexists with macroscopic irreversibility because the bookkeeping burden is grotesquely large. This link ties quantum mechanics to thermodynamics. Heat death, aging stars, melting ice, all trace back to the one-way leak of phase information into degrees of freedom we cannot corral. Time's arrow is not painted on the laws, but on our inability to gather scattered quantum breadcrumbs. If decoherence is entropy's advance guard, quantum error correction is the counteroffensive. The short code, surface codes, and cat codes distribute a logical qubit across dozens, or soon thousands of physical qubits. Local noise may flip or deafus some members, but parity checks catch and repair errors before they metastasize. In 2023, Google's Sycamore 2 maintained a logical qubit for an unprecedented millisecond, still brief, yet 50 times longer than its naked counterparts. Bosonic cat codes in 3D microwave cavities have lived hundreds of milliseconds. They're alive, plus dead photon cats, periodically refreshed by autonomous feedback. Each milestone nudges quantum processors toward the fault tolerance threshold, the point where error correction wins the war of attrition against the environment. Paradoxically, watching a system relentlessly can also freeze it, a phenomenon dubbed the quantum Zeno effect. Bombard a radioactive nucleus with rapid-fire measurements and its decay slows. Held in limbo by the very gaze that would reveal its fate. More practical is dynamical decoupling, timed pulses that flip a qubits. Phase-making environmental noise cancel like alternating Tugavour poles. In nitrogen vacancy diamond sensors, Carpacil MyBoom gill sequences stretch coherence from microseconds to seconds. Letting the same crystal probe neural currents or map nanoscale magnetic textures. Nature, too, negotiates with decoherence. Photosynthetic complexes coupled just strongly enough to sample multiple energy pathways, yet swiftly hand off excitons before thermal vibrations dissolve coherence. Migratory birds protect spin-correlated radical pairs inside protein cages, extending entanglement to the microsecond window needed for magnetic sensing. On the engineering front, silicon foundries now grow crystals 99.999% free of spin-carrying silicon-29 isotopes, quelling hyperfine noise for electron spin qubits. Superconducting circuits incorporate purified tantalum to curb two-level defects. While levitated sphere interferometers chill nanoparticles with laser feedback, so environmental kicks arrive only every few seconds. Long enough, perhaps, to glimpse macroscopic superposition. Add these threads together, and the message sharpens. Classicality is a crowdsourced illusion. When countless fragments of the environment store identical copies of a pointer state, observers, humans, cameras, dust grains, sample overlapping subsets, and agree on facts, what they can never access is the lost phase information that once linked alternatives, now dispersed beyond recall. The sun appears simultaneously round to billions of eyes, because photons streaming from its surface encode that shape redundantly across the solar system. Quantum drafts of non-round suns certainly existed, but decoherence ranked them unfit. They could not broadcast a stable headline. Our deterministic common sense is, therefore, a weighted average of quantum possibilities, filtered by survival in the open informational marketplace. With this, our exploration of quantum foundations reaches its final curtain. We have met uncertainty, superposition, entanglement, and the environmental tide that hides their spectacle. All that remains is to reflect on what these layers reveal about meaning, memory, and wonder in outro, painted in probabilities but read as lived experience. Stand beneath the night sky and breathe in the quiet. To human senses, the universe feels immovable, stars fixed in their constellations, mountains anchored to the crust, history scrolling one frame at a time. Yet every photon in that starlight, every atom in those rocks, every heartbeat in your chest is balanced upon a scaffold of quantum possibilities. Drafts the cosmos keeps revising faster than any mortal eye can see. We began our journey with a single question posed by a beam of electrons. Could reality travel to paths at once? The double-slit answered in ripples, yes and yes again. From there we followed uncertainty's restless hum. The rule that refuses pinpoint perfection so atoms may endure and galaxies may form. We watched superposition expand the universe's imagination, letting energy explore multiple futures before settling on one. We threaded entanglement between particles light years apart, and learned why those hidden webs rarely glitter in daylight. Decoherence. The world's relentless gossip, scattering information until classical certainty emerges as communal rumor. Together, these principles reveal a universe that is not optional. Not a polite veneer atop clockwork gears, but the gears themselves chromed in probability. Lubricated by phase, turning in silence until observation gives them voice. The chair beneath you, the bloodstream within you, the flame billions of kilometers away in the sun's core. Each is a story that might have unfolded otherwise, Had quantum dice rolled a different way? And still, wonder grows. Engineers coax qubits to balance on quantum tightropes, building computers that will map proteins in hours, forecast climate in clarity, perhaps even crack the secrets of high-temperature superconductors. Astronomers listen for gravitational murmurs etched in space-time by primordial quantum foam. Biologists discover that the robin's midnight compass and the leaf's morning harvest both lean on fleeting entanglement to survive. In every discipline, what once felt like paradox now reads as opportunity. To call the quantum world weird is to admit we have measured it with rulers forged from everyday instinct. Replace those rulers with curiosity, and weirdness reframes as depth, an ocean whose swells and undercurrents sculpt every shoreline of existence. Dive deep enough, and you will not find chaos. You'll find coherence wearing masks. Probabilities weaving patterns so vast that life itself can walk upon them without ever noticing the threads. So the next time you look up, remember, the starlight striking your retina left its home millions of years ago as a superposed whisper, tunneled through interstellar dust by uncertainty, arrived as a photon whose twin may be entangled with a grain of cosmic dust you will never meet. In that single moment, history, chance, and observation converge, and reality, ever accommodating, chooses one of its many drafts to lay at your feet. This is Cosmic Canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, never stop wondering.